Hi, we are going to choose the inductor for our buck converter, and in this case we have some previous comments before we see the rules for choosing the inductor. First of all, it's important to know that in general, in power electronics, inductors are custom-made components. However, especially for low voltage applications, we can find some manufacturers, such as Coilgraph or Würth, that offer a lot of inductors for different specifications. So, taking into account that in this project we want a simple approach, we are going to choose an inductor from these manufacturers. The penalization or the drawback of this approach is that the data sheets of these devices, of these inductors, are incomplete. So, for instance, we are not going to be able to evaluate core losses. In this way, we are going to represent the inductor, the real inductor, with a simple model like this, where we have the ideal inductance in series with a resistor that is modeling the resistance of the winding. This is a parameter that we can find in the datasheets. Okay, so let's see the rules for choosing the inductor. The first one is quite simple. The saturation current must be equal or higher than 1.5 the expected maximum instantaneous current. Okay, we already know the inductor current. We have seen this waveform in a lot of videos before this one. And well, remember that we measure this current in this way. And in this case, we have to analyze this peak, and basically the maximum current through the inductor. This is something that we did before, and the expression for this maximum current through the inductor is this one. We have the output current, which in our case is 15.15 amps, plus the peak-to-peak current ripple through the inductor, 3.03 amps, divided by 2, and this is equal to 16.67 amps. We multiply this quantity by 1.5 and we get 25 amps. So basically we need an inductor whose saturation current must be equal or higher than this quantity. Well, the second rule is also about the current through the inductor, but in this case is about the RMS value. So the rule is the maximum RMS current through the inductor. This is the part of the is a characteristic of the inductor we are going to choose, must be equal or higher than 1.2 the expected value. In this case, I have reduced a little bit this coefficient. What is the expected value? What is the RMS value of this waveform? Well, we are going to do a simplification that is not very important. We are going to consider that this inductor current ripple is negligible in comparison to the average value, which is something that is quite true if we consider our specifications. And in this way, the RMS value that we have in our circuit is the output current. The value is 15.15 amps. We multiply this quantity by this coefficient, and the value we have is 18.2 amps. So we need an inductor able to drive this amount of RMS current, okay? This value or a higher value. Well, so once we know that, we can go to Google and look for an inductor that satisfies these conditions. My recommendation is to directly go to Coilgraph or Würth websites and put the requirements and see what inductors they offer. And well, in my design I have considered this specific inductor from Coilgraph. The inductance, the nominal value is 8.2 microhenries, is higher than the theoretical value we require, because the theoretical value, I think that it was 7.9 microhenries. But if we increase the inductance, we reduce the peak-to-peak current ripple, so there is no problem. It's something that we can do. And regarding the resistance of the windings is 5.2 milliohms. Then we have the self-resonant frequency is 12 megahertz. So it means that if we work with a frequency equal or higher than this value, we will have the impact of the parasitic capacitors of the inductor. But since we work at a frequency that is much smaller, at 100 kilohertz, we will not have any problem with the parasitic capacitances. Well, the saturation current for a 30% drop of the inductance is 25 amps, is okay. And the maximum RMS current for a temperature increase of 40 degrees is 28.7 amps, which is also okay. And if you consider the dimensions that you see in the datasheet, the size of this component is this one. Okay, last point, how we put that inductor in our LTspice circuit is very simple. In fact, it's the simplest component that we have seen until this point. We only have to put an inductance or an inductor, ideal inductor, in series with a resistor. Here we put the expected inductance, the inductance according to the datasheet, and here we put the resistance of the windings. Very, very simple. Okay, so with this we finish with the inductor. We have another video talking about the output capacitor, and we finish with the selection of the devices. So see you.